AP Chemistry. This is the last lesson, lesson 4 of the electrochemistry unit. It's on electromotive force. So up until now, we've talked about the flow of electrons from an anode over to a cathode. In the example we've been using, zinc was the anode. It will give up electrons to copper according to the activity series, and it will pass electrons over to copper. So if you put them in two different cells and connect that cell with a wire, then the electrons will pass through that wire, and that flow of electrons is called electricity. How much they want to move, how strongly they want to move from the anode to the cathode, is a function of something called voltage. It's the push. It's how much push is on the electron. So let's read this. So voltage is electrical potential. Voltage is comparable to the gravitational pull of a planet. So just as the Earth will pull on an object with mass, a voltage, an electrical potential, will pull on charged particles such as electrons and protons. In an electrochemical cell, voltage is a numeric measure of how strongly the cathode, that's the copper in the earlier example, will pull electrons away from the anode, that's the zinc in the example. Another name for voltage used in chemistry is electromotive force, or EMF. All right, so here's the activity series. We've been using that for some time now, going back to lesson 35. So the activity series shows the oxidation half reaction for some metals. So it shows how an atom, a neutral atom, will give up electrons. So lithium, for example, will give up one electron to become a lithium 1+ ion, whereas barium will give up 2 electrons to become a barium 2+ ion. And we learned how to figure out what those charges would be. You could check either your 60 common ion sheet, your charge number by ion sheet, or just look at the periodic table. And if the element is in the first 2 columns of the periodic table or the last 6 columns of the periodic table, you ought to be able to figure out how it's going to ionize, whether it's going to lose or gain electrons and how many. Go back to the earlier unit, the fundamentals unit, and you can review that. So the activity series shows only individual elements, as you can see, not reactions. So the standard reduction potentials, and this is, there's one of these in your textbook in chapter 20. There's also a more extensive one in appendix, I believe it's appendix D in the back of your book, where it gives these reduction potentials for not only individual elements and molecules, but also chemical reactions. We'll try to keep it simple here and just stick to individual elements or molecules. So standard reduction potential, let's talk about what that is. Reduction potential is a fancy name for EMF or voltage. It's how much difference there is between the cathode's pull and the anode's potential and the cathode's potential. That's how much the electrons will want to move. It's essentially the voltage that you're going to get. And you can see at the top in the upper left, it says E, little circle, red, and then V. So that is a voltage. So the reduction potential standard simply means under standard conditions, which is 25 degrees, 1 molar concentration if it's a solution, or 1 atmosphere of pressure if it's a gas. So you want to compare all reactions and all of these types of reactions under the same conditions, so you get a sense of, you can compare, similar situations to each other for different reactions under the same conditions. Not all the time are you going to do these reactions under standard conditions, but at least you can put these in a table and you can compare them. Okay, so the standard reduction potential here is E with the little circle. That means standard at those conditions that I mentioned just a minute ago, and red means reduction. So this shows the voltages of different elements and ions and common reactions. Okay, now a potential difference has to be between 2 different numbers. So what are they comparing this to? So we'll talk about that. So standard oxidation potential, as opposed to standard reduction potential, can be obtained by reversing the direction of the reaction. You just flip the reaction around the arrow, and then you change the sign on the standard potential. So, for example, the very top one, which is a fluorine molecule, gives away 2 electrons to become 2 fluoride ions. That has a standard reduction potential of plus 2.87. If you flip that reaction around, then that would become a standard oxidation potential of negative 2.87. So the oxidation and reduction potential for each of the following reactions is defined as, and let me put those 2 reactions up, as the standard reduction potential equals the standard oxidation potential equals 0 for these 2 reactions that you're looking at. In other words, the standard is set against hydrogen ionizing. So the first reaction is you have a hydrogen molecule, an electrically neutral hydrogen molecule, and what it does is it breaks into 2 hydronium ions and gives up 2 electrons. And that has a standard, that would be an oxidation, and that has a standard oxidation potential of 0. Now, if you turn that around, you take the 2 hydronium ions and add 2 electrons to it, you get back to a neutral hydrogen molecule. That's a reduction. That has a standard reduction potential of also 0. So all the numbers you see on that table over there are compared to hydrogen. They're set against hydrogen. Why is hydrogen 0? Because scientists just decided to set that as 0 as the standard. Think of the centigrade temperature scale. Somewhere along the way, scientists just decided that the freezing point of water is going to be 0 degrees centigrade, and every other temperature is measured against that. So hydrogen is the standard by which all the other potentials are measured. All other voltages, or EMF, are measured against the ability to reduce to hydronium H plus ions or to oxidize H2O plus ions. So those are both considered to be 0 volts for hydrogen. An oxidation or reduction reaction will happen spontaneously when the standard potential voltage is positive, or when any voltage is positive. So those reactions, as you see them written up at the top, up above hydrogen, will all happen spontaneously. They will naturally give off electrons and therefore become ionized. Those would be reductions, okay? Now down below the hydrogen, where you see the 0, those are negative numbers. That means those won't happen spontaneously as a reduction reaction. What you'd have to do is turn those around and make those numbers down below hydrogen, down below that 0, you'd have to make those positive. So those would happen spontaneously as oxidation reactions. So up above the 0, they naturally happen as you see them written as reduction half reactions. Down below, you'd have to turn them around, make them oxidation half reactions for them to happen spontaneously or naturally. Okay, so we're going to continue with our example of using copper and zinc. So let's look at copper. So copper, we know that what copper is going to do is it is going to be reduced. It's the anode in our electrochemical cell. It's going to be reduced, so its oxidation number goes from 2 down to 0. And what we see is it's just up above hydrogen there, and that's going to give you a potential of 0.34. So copper naturally wants to be reduced compared to hydrogen, and so that's what it's doing in our electrochemical cells. It's receiving electrons, therefore becoming neutral copper atoms. Again, go back and review a couple lessons back where we talked about this. And so now we're putting a number to that, and that would be positive 0.34 volts. And so that means it happens spontaneously because that voltage is a positive number. Copper will spontaneously gain electrons and be reduced to H plus ions. In other words, it will be reduced against hydrogen. So if you compare it to hydrogen, it will be reduced. So this means hydrogen will spontaneously be oxidized. Okay, so if you put it in a solution with hydrogen, the copper is going to gain electrons, and the oxygen, or the hydrogen rather, is going to lose those electrons. So there's the reaction. So there's the oxidation reaction for hydrogen. And so it's going to go from an H2, which is a 0 oxidation number, up to an H+, which is a 1 oxidation number. Okay, now we're going to look at the zinc side of our electrochemical cell. So an oxidation or reduction reaction will happen when the standard potential, that is the voltage, is positive. If it's positive, it means that reaction is naturally going to happen. It's going to happen spontaneously. So here is zinc written as you see it on the table there as a reduction. That is to say that a zinc cation is going to gain 2 electrons to become a neutral zinc atom. Well, that's a negative number. It's a negative 0.76. That means that's not going to happen naturally. Remember, in our electrochemical cell, the zinc gives off the electrons. It's in the anode and it gives off the electrons. So zinc here in this reaction is shown as taking in electrons. That's not going to happen naturally. So that's why the voltage or reduction potential is a negative number. So the standard potential of reduction is negative, which means that the zinc will not gain electrons when it's in a solution with hydrogen atoms. If the reaction is reversed, however, then the standard potential of oxidation, you turn that reaction around, then the reaction becomes an oxidation reaction. That is, it's giving off electrons, will be positive, and zinc will oxidize to lose 2 electrons to the hydronium. So there is zinc written as an oxidation reaction. That's the way that it actually works. So you have a zinc atom. This is what happened in our electrochemical cell. You have a neutral zinc atom. It gives away 2 electrons that went across the wire over to the copper, if you remember. And that's spontaneous, so it's a positive number. It's a positive 0.76. Okay. So now we're going to put both of those last 2 slides together. So an oxidation or reduction reaction will happen spontaneously when the reduction potential, which is the voltage, is positive. So here what we're doing is we're taking zinc and we're oxidizing it, which is what zinc naturally wants to do, to hydrogen. It wants to give away 2 electrons and become a zinc 2+ cation. Those 2 electrons will jump over to 2 hydronium ions and make them neutral. It will turn them into hydrogen atoms, neutral hydrogen atoms, which neutral hydrogen atoms always get together and join up to become a hydrogen molecule. That's an H2. So you see that the reduction potential for the zinc, that's oxidation potential, is a positive number. That means it naturally wants to oxidize. And the reduction or oxidation for hydrogen is 0. It's set at 0. Now let's go down and look at the, let's read this first. The zinc spontaneously oxidizes and loses 2 electrons to the hydronium. Now let's go down and look at the reaction. We're going to turn that hydrogen reaction around. And we're going to turn it into an oxidation reaction where you take a neutral hydrogen molecule, it gives away 2 electrons and turns into 2 hydronium ions. Again, even in the reverse direction, the potential, the standard reduction potential is 0. So either way, that hydrogen equation has a 0 voltage. Now we're going to look at the copper. Copper naturally wants to be reduced, copper ions. So you have copper 2+ ions. They take in 2 electrons and become a neutral copper atom. Again, go back and look, review our electrochemical cell a couple of lessons back, and that's what we talked about. So what it says here is copper spontaneously reduces and gains 2 electrons to hydrogen, okay, or gains 2 electrons from hydrogen, it should be. Okay, so look at those 2 hydrogen reactions in the middle. They cancel out. They're the reverse of each other. They both have 0 potentials, so they just cancel out. So you can eliminate those 2 reactions and just put the zinc and the copper reaction together. So let's go ahead and see that. So an oxidation or reduction reaction will happen spontaneously when the standard reduction or standard potential voltage is positive. So there's the zinc reaction, and there's the copper reaction. We got rid of those two hydrogen reactions because they just canceled out from each other. So now what you see is you have 2 spontaneous processes. Both of these standard potentials are positive. So zinc naturally wants to oxidize, that's a plus 0.76. Copper naturally wants to be reduced, That's plus 0.34. So now when you put those two together, you just add them up and you get a standard potential for that entire reaction, the one that we did with the electrochemical cell a couple lessons back, the zinc passing electrons over to copper. You get a standard potential of the reaction of plus 1.10. And this is a fixed number. It's a number that's published that will happen when you put zinc and copper together like this. That number will always be 1.10. All right, now that's at standard conditions. That means your solution is 1 molar. In both cases, for both the zinc solution and the copper solution are both 1 molar, you will always get 1.1 volts flowing or pushing the electrons from the zinc over to the copper. So both the oxidation of zinc and the reduction of copper happen spontaneously. The standard potential of a reaction can be expressed in either of the equivalent equations. And there's one of them right there, actually. So the E of the reaction is the standard potential of reduction of the cathode. That would be the copper, plus the standard potential of oxidation of the anode. That would be the zinc. Okay, so you can express it that way. Okay, so the standard potential of a reaction can be expressed in either of the equivalent equations. So I kind of duplicated this here. So there it is. It's going to be the reduction of the cathode. So that's the number you get off that table that we had on a couple of slides back. You would get that number directly. That's the copper number. For the oxidation of the anode, that's the zinc. Remember what we had to do? We had to turn that around because zinc doesn't naturally want to reduce. So, and that table back there is showing the reduction of zinc. So zinc naturally wants to oxidize, so you have to turn that reaction around and change the zinc number from a negative to a positive. Okay, and that's what we did on the last slide. We made it a positive 0.76 rather than a negative 0.76. The standard reduction potential table lists reductions only, so this equation can be written if you want to do it this way. Understand this is the same equation, that the standard potential of the reaction equals the reduction of the cathode, what we have up in the equation above, but now what you simply do is you say minus the reduction of the anode. In other words, the zinc is shown as a reduction reaction. It really should be an oxidation, so instead of adding it, you're subtracting it. It's just playing with the equations. It's the same thing. You just got to remember that the oxidation side of the reaction, if you get it off of that table of standard reductions, you're going to have to turn the number around. You're going to have to reverse the sign on the number. So this form of the equation has a subtraction sign. If you use this equation, you won't need to change the sign on the number for the standard table of reduction potentials. In other words, you could have left the zinc number as negative, and then you subtract a negative. That's same as adding a positive. Okay, so there is our diagram again of our electrochemical cell. So on the left, the zinc is being reduced. It's giving up electrons. They're flowing through the wire, and they're going over to the copper. And you can see the equations down below, that you take the E oxidation, that would be the zinc, make it a positive number in other words, and the E reduction for the copper, that's a positive number, and you go ahead and add those, you get 1.1, and so that's what you would read on a voltmeter, which is a device that measures voltages, and you see that up at the very top. Okay, so the voltmeter would read 1.1. So let's read this. The anode is being oxidized, that's zinc, so use the reverse of the reduction potential from the table, which turns the negative 0.76 volts into a positive 0.76 volts. Okay, so go back to the table. Zinc is negative 0.76 on the table. And that's a reduction table, so since you need zinc to be an oxidation, you turn the equation around and make it a plus 0.76. Okay, not a difficult concept, just a little tricky at first. So there's the oxidation of the zinc. It's a positive 0.76. Now over on the right side, the cathode is being reduced. That's the copper. So use the reduction potential from the table, which is positive. So it is a table of reductions, and the cathode copper needs to be reduced in this reaction. So you just take the number directly out of that table. It's a positive 0.34. And so you add those two together and you get the total voltage of that electrochemical process that you see there. So the E reduction of the cathode is plus 0.34. And there we go. And that just shows the equation and shows how we got there. Now, free energy. We're going to relate this back to the thermodynamics, the last unit that we did. That's delta G. Delta G is a quantity that determines whether a physical process, such as a chemical reaction, will proceed spontaneously, naturally. We already learned that a redox reaction will be spontaneous if the standard potential of the cell is positive. So if it has a positive voltage, it will be spontaneous. So the relation between the EMF and standard free energy, delta G, standard, again at those standard conditions, 1 molar, 25 degrees, is this equation that you see here. So let's go back and review what did we learn back in thermodynamics. What would make a spontaneous reaction? It's if delta G is negative. When delta G is negative, any kind of reaction means it will go from left to right. It will proceed spontaneously. So let's state that together. So if the voltage is positive, that will be spontaneous. If the delta G is negative, that will be spontaneous. So that's the relationship you're going to see here. So the standard delta G, that standard free energy, equals negative N. The N is the number of moles, and that's simply in the case of our zinc-copper reaction is that 2E minus. It's those 2 electrons, in other words. You can think of that as 2 moles. So it's simply that number for N is going to be a 2. F is something called Faraday's constant. It's just a standard constant number. We'll talk about that in a second. And E is the standard potential of the reaction, in this case the 1.1 volts that we got on the last slide. So N is the number of moles and electrons. This is the 2E minus in our zinc-copper cell. F is called Faraday's constant. It's how many coulombs of electric charge you get per mole of electrons. That's very simply what it is. And there it is. It's 96,485 coulombs of charge, electrical charge, in 1 mole of electrons. That's called Faraday's constant. And then there's the standard EMF of the reaction. So this was the 1.10 volts in the zinc-copper cell. Okay, in the zinc-copper electrochemical cells, the following half reactions took place. Okay, so there we had that one and that one. Okay, so we're familiar with that now, and that gives us the 110 volts. Substituting the values from the zinc-copper cell into this equation right here that relates free energy with the EMF, with the voltage. So there, just convince yourself that is all the numbers plugged in. You have 2 moles, that's the 2 electrons. You have Faraday's constant there, and then you have the voltage that we got from this particular reaction. When you do the math on that, you get negative 212,267, and that's Coulomb volts there. And that we're not going to go into the details of this, but that simply is joules. It's the equivalent of joules. So joules equals 1 Coulomb volt. So you get a negative 212,267 joules for free energy. Again, since free energy is a negative number, that means this reaction is going to happen spontaneously. So again, positive voltage is spontaneous, negative delta G is spontaneous. That means they'll happen naturally. So there's that number. And I'm just making that note that 1 joule equals 1 Coulomb volt. So an electrochemical cell reaction will be spontaneous when the standard potential of the reaction is positive and the delta G is negative. And we see both of those things here. This means electricity will flow. In the zinc-copper electrochemical cell, we computed the standard potential of the reaction as follows, and there we had that. So remember, the standard means standard conditions. So 1 molar, that's 1 molar concentration of your solutions, both of them, both on the zinc side and on the copper side in our example. Or if it's a pressure, it's 1 atmosphere of pressure, if it's a gas. And generally it's 25 degrees centigrade. It does not have to be. The official definition of standard conditions does not include that, but almost every time you say standard conditions, you mean 25 degrees centigrade or 298 Kelvin. Okay, So the answer that we've gotten in those last few slides, the 1.10, does not account for values other than standard conditions. In other words, what if you don't want standard conditions? What if you don't want both of the solutions to be 1 molar concentration? So what if we want the EMF at non-standard conditions, meaning not those up above? So this is something called the Nernst equation. The Nernst equation allows for the calculation of voltage at non-standard conditions. So here's the Nernst equation. Now we're going to do a little bit of math here that you don't really need to know. What you want to know is this final equation, but that's the Nernst equation. Now generally most books, including your textbooks, convert that. So let me read this. Your book expresses the equation in terms of the common log, log, which requires the following adjustment to the equation. You have to put that 2.303 in there in order to change from natural log ln to common log log. Okay, so that's the first adjustment they're going to make. So the E is the standard EMF defined earlier. The R is the gas constant. Now if you go back and review gas constants, there's 2 of them. There's the one that we use with PV equals nRT. That is 0.0821 liter atmospheres over mole Kelvin. That's the one you use with PV equals nRT. This is the other one, and the difference is that rather than have liter atmospheres up in the numerator, you can see there that the 8.31 has joules in the numerator. Moles Kelvin is still on the bottom, but it uses joules. So this is the one you need to use when you're working in joules. Okay, the temperature, now even though we said we're not going to deal in standard conditions, they're still going to keep the temperature at 298, which is 25 degrees, pretty much standard temperature. What we're going to change is the concentrations here. Okay, there's Faraday's constant, and N is the number of moles. So again, in our example of zinc and copper, it's those 2 electrons or 2 moles of electrons that are being passed over. Okay, so again, we're going to do some math you don't really need to know. We're going to take that 2.303. The R is a constant number. The T in this case is a constant. It's 298. And Faraday's constant down on the bottom is a constant. So you can just wrap all those into one single constant number. And that number is over there, way over there on the right. It's 0.0592 volts if you put all those numbers together. So that simplifies the Nernst equation down to the one you see right there at the bottom there. It just makes it a much simpler equation to work with. Okay, now we have to deal with that Q, and you have to go back to the equilibrium unit to remember what Q is. It's called the reaction quotient. It's computed the same way as an equilibrium constant. That is, you use the law of mass action to do it, but it's not necessarily, the concentrations are not necessarily at equilibrium. And that's the whole point of the Nernst equation. There's some other concentrations that aren't necessarily at equilibrium or at standard conditions. So there's the Nernst equation. So going back to the equilibrium unit, the value of the reaction quotient Q is calculated the same way as the law of mass action. So there's our electrochemical cell reaction. We take zinc, it gives away 2 electrons to copper ions. The copper ions then become a copper atom, Cu, and the zinc becomes ionized at 2+. So that's our electrochemical cell reaction. So although I didn't write the states here, and I should have, the zinc, Zn, and the copper, Cu, are solids. And so they're solid atoms. They go into those strips, the copper strip and the zinc strip. So therefore, they're solids. You don't include them in the law of mass action. The only thing you include are the aqueous Cu2+ and the aqueous Zn2+. Go back and look at the electrochemical cell a few lessons back, and you'll see that the copper 2+ is in solution, it's aqueous, and the zinc 2+ is in solution, it's aqueous. So the only thing that goes into computing the reaction quotient is the zinc over the copper. Okay, the concentration of zinc over the copper will be that. So now we're ready for an example. So example, what is the EMF with the following concentrations of zinc and copper in the electrochemical cell? So now we're not dealing with 1 molar anymore. That would be standard conditions. Now we have copper, which is a lot more concentrated, and that's 5 molar. And we have zinc, which is not as concentrated, that's 0.5 molar. So now we're going to plug that into the simplified short form Nernst equation here. So these are not standard conditions, so we use the Nernst equation. There it is. and convince yourself that that's what it should look like. The N is 2, that's the 2 electrons. You have the concentration of the zinc up on the top, and you have the concentration of the copper down on the bottom. Again, it's products on top and reactants on the bottom. Okay, and then you just have to do the math on that. Be careful, don't make a mistake. And you get that the potential now, it went from 1.10, which it was under standard conditions, to 1.16 voltage. So why did it do that? So explanation, since we have a high concentration of Cu2 plus to gain electrons that is reduced, more voltage is produced. Okay, real quickly, we're just going to define the other kind of cell. What we've been talking about this entire time is a battery that produces energy. It's called a voltaic cell, or the other name that we don't use, I didn't use very much other than define it, is a galvanic cell. Voltaic and galvanic cells are the same. Now we're going to talk about a different type of cell. It's called an electrolytic cell. An electrolytic cell is a backwards battery. Whereas a battery produces energy, an electrolytic cell produces a non-spontaneous reaction that requires energy input to do work. So you've got to put energy into this to make it do some form of work that you want it to do. And I'll just give you one simple example. An example of electrolysis, which would be done by an electrolytic cell, is the plating of silverware. So silverware is not really silver, but they put either chrome or zinc on it to make it look silver, and that produces the shiny surface. So it takes energy to do that. You have to put energy in. So again, you do that through the process of electrolysis. And so it's kind of a backwards battery. Other than that, that's all we're going to say about it now. Maybe we'll talk a little bit more about it in the spring, but that's all we have for that. Okay, so that takes care of this lesson. Lesson 4, the last of the electrochemistry unit. So hopefully you have an understanding of how batteries work. You can explain this. Remember, on the AP exam, explanations are really the important thing, that you be able to express in words what's going on. Okay, that's great. We'll see you, talk to you on the next lesson or some future lesson.